The two-sample t-test is most commonly used to test the null hypothesis that two population means are equal, although it could also be used to test the null hypothesis that a difference in population means is equal to a specific value. The conditions are two independent simple random samples and normal populations. The formula looks like this if you're testing that hypothesis up there. X bar 1 minus X bar 2 divided by this big standard error expression. If you're testing the null hypothesis that mu1 minus mu2 is equal to a specific value, then you'd want to subtract that specific value in the numerator here. But that's not very commonly done. The degrees of freedom in this case could either be the smaller of n1 minus 1 or n2 minus 1, or it could be calculated from a computer or your calculator. If you perform this test on your calculator, it's a stat test 4 two-sample t-test. Let's look at an example of how this works. Can taking a calcium supplement reduce blood pressure? A randomized double-blind trial of 21 subjects, divided them up into a group of 10 which received a calcium supplement for 12 weeks and 11 which received a placebo. These are the calcium reductions for those 21 subjects. Do these data provide evidence that a calcium supplement is more effective than a placebo at reducing blood pressure? Well, whenever you do tests of significance, you want to start with your hypotheses. In this case, the null hypothesis is that mu1 equals mu2. That is, the mean decrease in blood pressure for those taking calcium is the same as the mean decrease in blood pressure for those taking the placebo. The alternative would be that the calcium supplement is more effective than the placebo and mu1 is greater than mu2. Conditions, two independent SRSs. Random assignment to treatment groups takes care of that. Normal populations. Stem plots for the data show that these data contain no outliers and they're consistent with normal populations. We don't have a normal populations given to us, and we don't have large sample sizes or group sizes, so we can't rely on the central limit theorem to bail us out. In this situation, we have to rely on the data. The data are fairly well behaved. For the placebo, symmetric, single-peaked, very nice. For the calcium group, somewhat skewed, but no outliers, and this sort of thing happens whenever you have a small group. If the group were larger, then perhaps things would fill out and look more like we'd expect them to look. But those data are consistent with coming from a normal population. These are the group sizes, the group means, and the group standard deviations. And we use those to make the two-sample t-statistic, which has this formula that we put up before, x1 bar minus x2 bar divided by this big standard error expression. When we plug everything in, the numerator simplifies down to 5.273. The denominator simplifies down to about 3.288, and our t-statistic is about 1.6037. Then we can go to TCDF on our calculator and figure out our p-value. It's about 0.0716. And in that situation, while that is small, it's not small enough to reject the null hypothesis at an alpha level of 0.05. The calculator, we used 9 degrees of freedom here, the smaller of n1 minus 1 and n2 minus 1. The calculator would use degrees of freedom of 15.59, and they would give you a slightly smaller p-value of 0.0644. In either case, whether you do this procedure by hand or whether you do it with the calculator, in both cases we would fail to reject. Now this suggests that perhaps there really is something going on here and the calcium supplement really is more effective than a placebo would be, but our sample sizes, our group sizes are too small, and so our test is not powerful enough to reject the null hypothesis if it were in fact false. There's a pretty good chance that we are committing a type 2 error here by failing to reject. And if we had a more powerful test, we would be less prone to that kind of error. And our summary or our conclusion is that I failed to reject the null hypothesis and failed to find sufficient evidence that the mean decrease in blood pressure for those taking calcium is greater than the mean decrease in blood pressure for those taking a placebo. Again, there's a pretty good possibility we're committing a type 2 error here. If we had had larger group sizes, then we would have had a more powerful test, and we would be less likely to make that kind of mistake.